Okay, recording started. Let me share the screen. Yeah, but first, before sharing, I need something to be shared. So, 1 second. Okay. Okay. Okay, so good morning again. Let's start with again with the lecture, which I just started last week, but very briefly. Inductive and deductive estimation of climate change and climate impact. Here we are. So, basically, so far we set the basis for evaluating the impact, climate impacts, okay, through the risk equation, risk-based adaptation design. And now it's the time to start discussing the solutions, and we started already to some extent when I discussed solutions for water resources management. But besides discussing the solutions, it's time to start to look at how solutions can be sized in practice. And in order to do that, we use again the risk equation. And in my premise, I pointed out that climate change is impacting in the risk equation the probability of the event. And in particular, you know that the probability is usually estimated through probability theory. And we had some discussion and refreshment of probability theory. The challenge here is to estimate the probability of the given event in the future and under a different climate. Because, of course, usually we estimate probability basing on experiments. Experiments in environmental assessment is usually done by analyzing observed data, historical data. These historical data refer to the past and current climate. Of course, we cannot perform an experiment, meaning observing processes in the future climate, because the future climate is still to come. And this is a relevant challenge. You know that probability can be estimated also basing on perceptions, but actually basing on a Bayesian approach. So what is our expectation, our subjective expectation? But actually we need to try to be, given that we are dealing with the project design, we have to try to be as rigorous as possible. And therefore, we can elaborate on our expectations, but we are also committed to find ways, objective ways to support the expectation with something that is factual, that is objective. And it's not only based on our feeling. Of course, we have feelings about the future climate. We have expectations. On the other hand, we have to corroborate these feelings with a quantitative assessment. And these are our commitments and our duty in engineering, but in general, in policy making. So let's indicate the future probability with the symbol hat P. Just 1 second, I look at, okay, at the end of the lecture. So basically, let me take a chalk. Let's indicate with the symbol hat P the future probability that we have to estimate. I use the symbol just to be clear, and in order to make a difference between, just let me check if the blackboard is in the screen. No, let me, yeah, here it is. And just to be clear, as I said, in order to make a difference with respect to the probability that we have defined in theory so far with the symbol capital P. Okay, so how can we estimate this future probability? First of all, let's say that in general, when we want to make an assessment of a future hazard, of a future probability related to climate, we may use two main categories of approaches. On the one hand, we can use inductive estimation. On the other hand, we can use deductive estimation. So inductive and deductive approach. Basically, the inductive approach is based on the analysis of facts, analysis of results. So basically, we refer to the outcome from a process, and then basing on the outcome, we make an inference on the process. So we start from the end, and then we go back trying to understand what is the dynamics of the process. Of course, in this case, for the future, we don't have outcomes, but we can, in a way, refer to the data analysis of the past, the analysis of historical data, and therefore refer to the outcome from the past and derive a guess, an estimate for the future outcomes. But the concept is that in the inductive approach, I based my assessment on the analysis of the outcome. I don't care about the theory, just to be very clear. In the deductive approach, conversely, we start from the theory, and then basing on the theory, basing on our understanding of the system, basing on our understanding of climate, we elaborate a model, typically a climate model, and then using the model, we make a prediction. You can use the same approach also for assessing the current situations. We know that we can estimate, for instance, probability basing on data, but we may also estimate probability basing on a model output. It depends on our needs. It depends on our also background, our inclination. Some people trust more models, so some people trust more the methods that are based on the theory. Other people trust more data. Usually, when you talk with engineers, they trust more data than models. When you talk to pure scientists, they tend to trust more the models. It's a question of different background. It's also a question of different professional commitments that these people have. So the scientist is committed professionally to gain a new understanding. The engineer is committed professionally to make a project, to elaborate a project, and to make sure that the project is correct. So basing on different needs, different backgrounds, different commitments, you may find people that prefer the inductive approach and some other people that prefer the deductive approach. So when we come to climate change, what is the in practice the difference between these two approaches? So we can estimate future climate by basing on climate models, and we already discussed the uncertainties, what are the pros and cons of this approach. Or we may try to estimate the future climate basing on analysis of historical data. So we look at past climate changes, and by, in a way, studying the past climate changes, we gain an expectation of what is going to happen in the future. So you understand clearly what are the limitations of the two approaches. Climate models are to some extent affected by uncertainty. At the same time, when you extrapolate into the future the results that were derived from past situations, the big question is, how can I make sure that the past changes will be the same in the future? You know that climate change has this big question mark. So the changes in the future climate will be similar to the changes that we have observed in the past, or will it be something completely different because of the human influence, because of the increasing atmospheric emissions? So you clearly see the limitation of the two approaches. And what is the solution? The ideal solution is to try to use both of them, and to try to use both of them and compare the results. And then, basing on our purpose, if your purpose is understanding, you may opt for trusting the climate model, because the climate model may give you something that is enlightening. But if your purpose, conversely, is to make a design project and to propose a solution that is doable, I mean, you may prefer a kind of estimation that is more practical, that is more fit to purpose. Ideally, as I said, if you compare the two solutions, you may decide whether you want to stay on the safe side, whether you want to stay on the practical side. It is not easy to apply both solutions because, I mean, the skills that are required to make a climate change impact assessment are specific and not simple. I mean, they are skills that, you know, in order to run a climate model or to evaluate the output from a climate model, you need a strong preparation on the subject. And at the same time, you need a strong preparation in statistics and probability to extend into the future evaluations that were derived by using past data. So sometimes it's not easy, and this is why we say it's not easy to get skills for integrating these two approaches in one person. And this is why we often say that interdisciplinarity is needed, and why a team working is needed. The ideal situation is where you assemble a team of people and you put together climate scientists, engineers, hydrologists, especially if the task is a relevant task and you have the resources for doing that. This is the ideal solution. But in any case, it's not simple, because people with different skills, different backgrounds, sometimes they have also problems in interacting. They use different terminologies. They have different targets, also in terms of promoting their personal career, which is something that is indeed important. In order to get the most from people, you have to give a recognition to people. And their career are based on different types of recognition. So it's really not easy to put people to work together. Also because, you know, usually people are busy. Okay, so we have these two possible approaches. Let's start to make some examples in order to answer to our question. So what is the future probability of climate? And let's start from the inductive estimation, okay? And this is a classical approach in climate impact analysis, the analysis of historical data. And historical data, you know, in any case, they are important. Even if you think that maybe the past is not representative of the future, data are nevertheless important, because even if you decide to use a model, if you have data, you can test the model in the simulation of past climate. And then you get an indication of the model uncertainty. This is something problematic, really problematic, testing climate models on the past climate. Now we see research contributions, an increasing number of research contributions that aim to do that. So to test models over the past climate. But it is really problematic. It is problematic because what are we comparing? What do we want to compare? We cannot compare, you understand, we cannot compare the model simulation of the climate of the meteorology in Bologna on February 4th, 1950, with an observation. This is not possible. I mean, we understand that we don't have the capability of doing that, because you need a precision that we cannot take from a climate model. And even if we had a model that was able to reconstruct the past climate for 100 years, day to day, you understand that the information that would be required to run the model is not available, because meteorology depends by barometric pressure, circulation, global circulation, and several things that we don't have. So clearly, it's not possible to compare day by day what happened. It's also not possible to compare year by year what happened. So if we compare the average rainfall over Bologna in 1950 with a model simulation, this is something that is not, it's not possible. We still don't have the capability of doing that. So what is the solution I anticipate? The solution is that people try to test the model statistics and the data statistics averaged over a long period, like 30 years, a climatic period. And even if you do that, you understand that models are not as good. And this raises really a big question, like how can we estimate model uncertainty for future predictions if the models are not able to reproduce the past? Okay, let's postpone this question. I just wanted to anticipate to you that data are important, at least for model testing. Model testing is an open question. So don't assume that climate models are reliable in the simulation of the past climate. This is, this is an open question. We got some preliminary results, but still it's a research challenge. Keep in mind that usually for an environmental scientist, in order to apply a model, testing is a basic requirement. And for an engineer is absolutely compulsory. So an engineer that applies a model without testing is subjected to mistakes and to sanctions. So in engineering is really a compelling requirement. So before applying a model, we need to test it. The testing may be done by the literature. For instance, I know that a model that I am using is a consolidated model because people use it and already tested it. So it's not necessary that you personally test a model. You can base on the literature, but you have a way to prove that you can trust your model if you are an engineer. If you are a researcher, it's a different story. Okay, so as I said, data are anyway important, and then we will discuss about model reliability more in the future. Let's start with the data analysis. There is a very simple way of making analysis of climatic data, which is trend analysis. Trend analysis is extremely simple. I am sure that you know what we are talking about and already, but I think that some refreshment is interesting because in refreshing the theory of linear trend estimation, I think I can highlight some specific features that are relevant in order to discuss the reliability of this kind of estimation. First, I said linear trend. Let's start from the linear trend, okay? And the linear trend is the simplest analysis that we can make. What is linear trend? It is linear trend estimation. Basically, you get some historical data. Let's suppose that you have temperature data, global temperature, okay? And let's say that here you have the global temperature. Let's indicate it with the symbol T, and here you have time. And let's suppose that we start from 1950, and then we get to 2024, okay? Here we are. And this is our global temperature. If here we have here more or less 1990, you know that the progress of global temperature more or less is okay, you have some fluctuations, but there is a period of global cooling, and then we had this steep increase in the past 35 years, more or less, okay? Of course, this is an approximation, it's not really, but you can find the graph of global temperature in several websites, and you get the right one. So what is linear trend estimation? Basically, I select a window, like this window here, okay? This is my time window. And then, over this time window, I interpolate the data with a straight line, okay? This is my straight line, more or less, okay? So let me just do like this and like this. So, okay, this is my straight line. And then for making a future prediction, I extrapolate. Very simple. Now, why this method is so popular? Because you understand what is the limitation of this method. You understand that we cannot blindly trust this extrapolation into the future. Okay? Because you see that, for instance, if you change the time window, the slope changes of this straight line, and therefore the future prediction changes. And what matters here is the slope. Okay, what makes the difference with respect to your future prediction? It's the slope. Okay, because usually we start from the last observed point and then we push it forward. So if you change the window, the prediction changes. And if you have an outlier here during the window, if you get an observation that is affected by a mistake, the slope changes, especially if the window is short. And you understand that, for instance, if you want to go into the future up to 2100, this is usually the window we refer to, we need to extrapolate for 75 years in the future. And if your window is 35 years long, from 1990 to 2024, you have a kind of intuition that extrapolating for, in the future, a window for 3 times, 2.5 times its length, it's not very reasonable. If you are, if you have some technical skills, you understand that if the window is short and it's shorter than the extrapolation period, there is something that may not be. So what is the reason why it is so popular? The reason why it is so popular is robustness. Robustness against uncertainty, robustness against outliers. If you estimate a straight line, you have only 2 parameters to estimate. Robustness means reliability of the method. Okay, and or let's say a robust method is defined as a method that is not very precise, but is not affected by huge uncertainties. And the reason why it is robust is that a straight line is characterized by only 2 parameters. I will write on the blackboard the equation of a straight line, but you can look on the screen here, you see. And yt is equal to a plus bt, okay? A and b are the 2 parameters. T is the independent variable. Y is the dependent variable. In this case, the equation may be like something like temperature at time t is equal to a plus bt. Let me see if the blackboard is still in the screen. Yes. And here I need to add an error term. Okay, an error term because the straight line doesn't reproduce the data precisely, and therefore I have to add an error term, which I call epsilon t. And so you see that I have only 2 parameters to estimate, A and B. So with only 2 parameters, if you use a long window like 35 years, you have at least 35 numbers to estimate 2 parameters. It's quite good. It is more robust, for instance, with respect to the polynomial interpolation. Polynomial interpolation, you put parameters at the exponent of time, and a small change of a parameter that is placed at the exponent translate in a big change of the prediction. Here, you see that a small change doesn't make a big difference. A small change in slope doesn't make a big difference. So this is why a linear trend is so popular. And it is indeed widely used. So we often see linear trend estimation for sea level rise. For if you go back to some of the slides that I presented to you, some of the pictures of the graphs, you see that in most of the cases you have a linear trend estimation. And let me just show you one of the figures that I already shown to you, the Po River at Ponte Lagoscuro, the series that you have, maximum annual maximum river flow. Look on the screen, and what you see running over the time series, it's straight line interpolation over a running window that is 50 years long. 50 years, it's a long time. When we make environmental assessment, climate assessment, and when we extend the assessment over 50 years, it's considered a long time. Nevertheless, you see that the slope is continuously changing. It's continuously changing, but this is a clear demonstration of the use of linear interpolation. And based on the linear interpolation, we say here the interpolation is mostly blue. It means that the peak flow is more increasing than decreasing during these time windows. So it is indeed a very good way of trying to assess changes and project them into the future. Usually, this method is used more for assessing past changes than for projecting into the future. Because, of course, when you refer to the past, the information is solid. When you extrapolate, it's less solid. Remember, anytime that you extrapolate a knowledge into the future, you have to turn on a light in your brain, like, this is something I have to be very careful of, even when you use a model, okay? So if the model, I said, need to be tested, but it's tested with respect to the past. When you use the model for the future, you are extrapolating, okay? Okay, so let's learn some more about the linear trend. First of all, what is a linear function? Linear function, I think, probably I already discussed with you the two criteria, the definition of a linear function. Let me write it on the blackboard because this is extremely important. You have to, when you talk about changes, you need to know what is a linear function, because many times you listen to somebody saying changes are linear, changes are non-linear. So a non-linear behavior, non-linear pattern in climate change is something more concerning than the linear pattern, okay? So you need to know what is a linear pattern. Just right here, and with the same symbol that you see on the screen. So let's call the function lowercase f, okay? So first condition, one, a linear function, linear f, okay? So f a plus b is equal to fa plus fb. And then second condition, f a at, I use t here or what? No, x, okay. X is equal to a fx. Good. This is a definition of a linear function. The first condition is called also the superposition principle. It means that if you have two changes of the independent variable, or a function of a plus b, the effect of a plus b is equal to the effect of a plus the effect of b. Okay. In general, the superposition principle doesn't apply in environmental assessment, in environmental systems. And think of rainfall, like the flood in the Romagna region. they got two heavy rainfall, which were, I think, 7 days apart, 7 days distance between the first and the second extreme rainfall. And we all know that the first extreme, okay, caused some damage, but not as much. I mean, not as much as the second one. The second one was a rainfall that was like comparable to the first one, but the effect was much larger. Why? Because it rained over the wet soil, the wet terrain. So when we say it rains over the wet, and you know it's a proverb, okay, it means that the superposition principle doesn't apply. Okay. Okay, this is the definition of the linear function, and fitting a linear function to data means precisely what was written before on the blackboard, and you see now on the screen, in the third equation. Means, let me write it here again, because I think it is with the same symbol. So yt is equal to a plus b t plus epsilon t. Okay. One thing, these two parameters are constant with respect to time. If they are not constant, it's non-linear. Okay. If A was AT, this is non-linear. It's non-linear because at this point, or let's say, you understand that the shape of the figure, the shape, the geometric shape that you get if A depends on T, it's not a straight line. Okay, and the same thing for the parameter B. If it depends on T, it's non-linear. So linearity means also that you get a straight line, okay, in the graph. So for instance, if you change the intercept, this is Y, and this is T. So let's suppose that you change the intercept. Basically, your function would be, for the first part, like this. And then you change A, and you bring A, this is A, okay? If this is 0, this is A. And then let's suppose that you change A. So you bring A here, okay? This is the new A. Let's call it A star. Let's say A star, okay? You bring it here, and starting from this point, then it means that your graph would become something like that. You keep the slope, but if you change the intercept, you have a step. This is not a straight line. This is a function that you can call piecewise linear, which means that you have the composition of two linear pieces, but overall, it's not linear. When there is a step, when there is a threshold effect, it's not linear. Okay, one nice thing of this linear function is that the estimation of A and B is quite simple. And it's quite simple. How can we estimate A and B if we have data? Okay, first of all, we need data. We need data of Y and with respect to time. The data of Y with respect to time, meaning a series of numbers collected during time, it's called a time series. Okay, time series. I think there is a link somewhere here. Time series. So let me open in another. Okay. And you see here an example on this graph. This is a time series. And you see that it's barely visible, but there is a black line that is a straight line fitted over the series. And then there are other, forget about the blue line and the red line. They are further elaborations of the time series. different from the linear interpolation. Okay, so you get this time series, and then you need to estimate A and B. Intuitively, you need to minimize the mistake, to minimize the error, to minimize epsilon. Okay, and why minimizing epsilon? Because ideally, if epsilon was zero, identically zero, my interpolation would be perfect. And therefore, we have to minimize epsilon. And however, to minimize epsilon, we need a rigorous approach. And usually we use the least squares approach. What is the least square approach? I minimize the sum of the squared epsilon. So let me write it here, okay? By using the same symbols. I search for the minimum of the summation between t equal 1 to, okay, summation of over I, and it means summation over time, okay, of, sorry, I note now that there is a mistake here. I write correctly over the blackboard. It's 1 over n, where n is the number of the data. So I'll make the correction soon. And 1 over n y I think it is more correct to write in this way. I equal 1 to n, it's the summation, okay? And here I write yi, and then I will rewrite also with the website, minus a minus b t. And then I square it. Let me see if everything is in the screen. 1 second. Yeah, it is everything on the screen. Okay, so let me just summarize once again. There is a mistake there, which I will correct. The summation is a standard over the data that I collected, and I indicated the index with I of the summation varying from 1 to n. N is the number of the data. And then I compute for varying I the difference between the observation, which is observed at time, okay? I in this case indicate the time, and minus the linear interpolation. So I am minimizing the sum of the squared errors, okay? This is called the least squares approach. There are statistical proofs proving that this approach for parameter estimation is reliable under assumptions. We make only a brief mention here to assumptions. What do I mean when I say that this is an estimation method that is reliable? It means that is statistically valid. I don't want to get into more details about this because statistically valid means quite lengthy definitions, which we are not interested in. But statistically valid basically means that this is the best way to estimate the parameters that you may find, that you may use. You may use different solutions, like instead of minimizing the squared difference between data and simulation, we could minimize the absolute difference. You should avoid minimizing the sum of the difference with sign, because negative error could compensate positive errors, which is not what you want. But if you minimize the absolute difference, it is analogous to minimizing the square of the differences. And however, we can demonstrate that this is more statistically valid under certain assumptions. What are the assumptions? And I don't like sticking on too many details related to assumptions, but I think in this case it is important. It is important. So The assumption, the main assumption is that the epsilon, the errors, are Gaussian, normal distribution. Once again, the main assumption is that the epsilon, the errors, are Gaussian. Okay? And you may think, oh, this is really boring. Why should I remember Gaussian? What's the matter here? However, there is a clear explanation of this assumption. If you think at what we are doing, we are squaring the error. So imagine that you have an outlier, an observation that is highly mistaken. It's already a huge mistake in itself, but if you square it, the mistake becomes squared. So you understand that squaring the differences is dangerous, because if there are data that are mistaken, you square the mistake. So why the Gaussian assumption? Because the Gaussian assumption, you remember the Gaussian distribution, it means that you don't have large outliers. The Gaussian distribution concentrates the numbers close to the mean. So if I assume that the epsilon are Gaussian, it means that I am excluding the possibility of getting an outlier. And you understand why. So what is the moral of the story? The moral of the story is that if you believe that your epsilon are not Gaussian, you should forget about the theory. You should forget about what the theory suggests, because when you have a situation where assumptions of a theory are not satisfied, you have to forget about the theory. If you are a technician, you have to find a technically valid solution. I say it once again because it is important. When you put the theory into practice, when we pass from the awareness of climate change to solutions, we have to be technically valid. So you have a theory underlying what you are doing, fine. You have to ask yourself, what are the assumptions of the theory? The assumptions are the limit of validity. If an assumption is not satisfied, you are going outside the limit of validity of the method. And this is not tolerable for an engineer, for a person working in practice. Okay? So basically, if you think that there are outliers, and this is what I normally do, like when I have to support policy making, okay, and I see, there are outliers in this time series, and then I may decide to use not the square, but the absolute difference. So you understand why I think it is important in this case to discuss the assumptions. Because if you use any method, this is the step that you should follow. Assumptions, checking the assumptions. Do you trust the assumptions? No. Try to elaborate your solution that is maybe better, or at least try to compare. Try to compare with a different solution. Okay. Now let me just open R console and show you how it is very simple to make a linear trend analysis by using any software, Excel, and it is so simple that any software that you may use has embedded a function for linear trend analysis. So you don't need to apply this equation directly, because here there is a bit of a problem. You have to search for the minimum, and searching for the minimum means that you have to try the different values of A and B and find the combination of A and B that gives to you the minimum. And this is operationally, it's quite complicated. And I mean, in principle, it's just trial and error. So you try, but you understand that when you have one parameter only, you can go with trial and error and you converge quite quickly. With two parameters, it becomes a little bit complicated, because you understand combination between A and B, you have to make several different attempts. And imagine if you had 10 parameters, how many combinations you have to try. It becomes impossible by trial and error. And therefore, about 30 years ago, a huge and intensive research activity started at the global level on algorithms for finding the minimum. And it was like 10 years, 15 years of research. And now it's so consolidated that any software has its own algorithm to look for the minimum. But even in R, you have several different alternatives, several different algorithms, because here the problem is the computational effort. When you have to try several combinations, it may take weeks. At the beginning, it took weeks 30 years ago. You had to leave the computer running for weeks. So the problem is the efficiency of the algorithm. Now they are so efficient that it's a matter of few seconds. Okay, now let me open our console. One second. I hope it's still there. Let me see. Because, you know, sometimes this PC undergoes some cleaning. I think it's not there. Let me just see 1 second. Okay. Okay, give me 1 second. I need to install it. And I need to do that because okay. Here we are. Just 1 second. I change the font. Okay, good. I clear the screen. Okay, now over the screen you see an R console. Let's generate a time series from the Gaussian distribution, and let's call it a time series. And we can generate, as you know, from the normal distribution with the function rnorm, and let's generate 1000 data. Okay, these are our data depending on t. And with mean 0 and standard deviation 1. Okay, this is our time series. And now let's estimate the linear. First of all, let me plot it just to show you the time series. Type equal line. Okay, this is the plot. So basically, you don't see big changes, and we don't expect changes. We expect data that if I fit a straight line, the slope is zero. Okay, the intercept is zero and the slope is zero. Intercept is zero because the intercept is on the mean value, and mean value I generated is zero. If you see mean of the time series, mean of time series, okay, time series, it's close to zero, okay? Now, the linear interpolation, let's call it lin trend equal to, I think the function is lsfit. Lsfit, I think I just need to give time series. Why? lsfit time, yeah, I made a mistake, sorry, time series. Okay. It wants an x and y. So time series is the x is an index that is a sequence between 1 and 1000. Okay, and time series. So it wanted the index, it wanted the time axis. So I put a time axis from 1 to 1000. Okay. So what I did is basically this. I put here, I generated these numbers. So here there is time series, okay, time series. And then here there is time t, and I put for time t a sequence between 1 and 1000. Okay, so time is starting from 1, not from 0. It depends on, it's your decision. Okay, so the linear trend estimation has been done. Okay, what is the result? The result is a list, and let's see what are the names of in this list. So the list is a collection of several variables into R, and at each variable is given a name, and you see these are the names of the elements of the list. I am interested in the coefficients. Okay, so lin trend coefficients. Oh, sorry. This is the name, coefficient. Okay, and here you see the result that intercept 0.08 and slope is minus close to zero. They are both close to zero. This is what I expected. However, as you can see, they are not zero. They are not zero. So even if I generated a series with no slope, no intercept, given that you are analyzing numbers at the end, you will never get 0, 0. Okay? What are you expecting, for instance? Let me repeat it. Okay, so let me generate another time series, and let me get another linear trend estimation, and let's get the coefficients. You see, they are close to zero, but not zero, and they are changed. Okay, so let me make it once again. 1, 2, 3. 1, 2, 3. 1, 2, 3. You see? Anytime I get a different result. Let me do it once again. 1, 2, 3. 1, 2, 3. 1, 2, 3. Anytime the result is different. So why I wanted to show you this? First, you see that it's extremely easy to make it. Second, you are left with a challenge here. The challenge is, how can I say that the slope is zero if I get a result that is not zero? So this is the challenge. Okay, so if I make climate assessment, climate analysis, and I make this linear interpolation on the past 1,000 years of global temperature, if I was lucky enough to get so many data, And then I get a slope, I look at the first one, of 0.0000031. Is this not changing, or it's changing? It's increasing, given that the slope is positive. Now, let me repeat the same computation with a series that is shorter. Okay, so let's clear the screen, and let's get 10 instead of 10 numbers instead of 1,000. And then, yeah, I made a mistake here. The sequence is 110. 1, 2, 3, 4. Now, let me repeat it, okay? Let me clear the screen because I want several results over the screen. 1 second. Okay, and okay, first result, second result, third result. Okay, what is the difference with respect to what I did before? The difference is that they are not so close to zero. There is a higher uncertainty here. Even if the model that generates the time series is always the same, so it should give the same results, and the model is a model with no change, you see the effect of uncertainty, which is higher as the size of your data decreases. So you need a criteria here, a criteria to estimate this uncertainty, and you understand why it is so important. Because if you extrapolate into the future, these results, you get, in the first case, a significant increase of temperature. In the second case, sorry, a significant decrease in the first case. It's negative. The slope is negative. In the second case, you get a significant increase of temperature. In the third case, again, a significant decrease. So the linear interpolation is robust, as I said, but still there is uncertainty. So how can you do then? How can you fix a criteria to be able to say that the slope is zero or not? So this is your question. Your question is, this slope, can I assume it's zero or not? In statistical terms, as you can see on my web pages, the correct formulation is, can I reject the null hypothesis that the slope is zero? So you have to fix an hypothesis, which is called the null hypothesis. Null hypothesis, the slope is zero. To remember the term, just consider no change, null hypothesis. The null hypothesis is that the slope is zero. Can I reject it or not? Of course, I am interested in this question. Can I reject the hypothesis that there is no change, that the slope is zero? So what is a trivial way of establishing such a criteria? What is a trivial way? You see that here I made it 3 attempts to estimate the slope and the intercept for a series of observations generated by a model that is respecting the null hypothesis. The slope should be zero. Okay, so I know that from the theory that the slope should be zero, and then I performed 3 attempts, and I get 3 different numbers. So the idea is to make a statistical experiment. I perform not just 3 attempts. I perform like 1,000 attempts from a model with no change, and then I can identify a range around zero of slope values. and this range fixes my interval. So let me try to be clearer. Let me write on the blackboard these steps. I generate 1,000 slope estimations. Slope estimations. Okay. Now, to compute probability density of estimates. Let me write it here, okay? These are my slope estimates, 1,000, okay? And their average will be 0, of course, because some numbers are positive, look at the screen, some numbers negative, and the average should be what I am expecting from the theory, 0, and then I will get a distribution around 0. Okay? Perfect. 3, identify the range where (95% of estimates fall. Okay, so it will be something like here, this range here. Okay, this is my range. Range 95%. Is this clear? Identify the range containing 95% of the estimates. Okay, and this 95% is called, this 95% is arbitrary. I could have identified the range with 90%, 80%. It's arbitrary. Usually, it is usual practice in statistics to identify uncertainty at the 95% level. This 95 is called the confidence level. So we introduced this terminology, confidence level. Okay, confidence level. So it is important because very often you may get uncertainty estimates at the 95% confidence level or 80% confidence level. Okay. And beware, if 95% confidence level, so 95% or confidence interval, very often it's called confidence interval or confidence band, confidence range, okay? This corresponds to 5% significance level. Significance level. Let me see if everything is in the screen. Yeah. So I want that you get familiar with these terms. Significance level, confidence level, they are like synonyms. They are not really synonyms. They are the complement to one of the other, or the complement to 100% of the other. So sometimes you may listen people saying uncertainty at the 5% significance level. it's the same uncertainty as the 95% confidence level. And you understand it is very simple how we estimate it. With the help of a computer, we can do it in a very simple manner. There is, in some cases, no need for simulation. In some cases, we have analytical theories. For instance, for the linear regression, for the linear interpolation, we don't need to make these simulations. If the assumptions are satisfied, if the data are Gaussian, we have analytical expressions for the confidence interval, confidence level. If the data, the assumptions are not met, then you may need to go with simulation. This is a very powerful way of evaluating uncertainty. Basically, I compare the results with something that is known, and keep in mind that the confidence interval depends on the specific application, meaning that if you perform the simulation with a different sample size, in this case is 10, but I have shown to you that with the sample size of 1,000, you get a different result. So beware of the fact that in this case, I made an exercise by generating from the Gaussian distribution and data that are not correlated, no memory, so numbers that are extracted individually, no memory, so temperature has memory. And Gaussian. So when you make a simulation like this one, you have to make sure that the statistical properties of what you simulate are the same as your data. So if I made the simulation to refer to a case, a practical case, where the data are not Gaussian, then the simulation is not valid. You have to make sure that the simulation is done with a model that is fitting your data. Okay. Let's forget this example. And if I go back to the web page, you see that there is written what I just said: confidence band, and then hypothesis testing, assumptions. Basically, you have anything written here. Okay, maybe that you find something more, but I don't think so. Confidence level, significance level, I don't think you find something more than that. So what is a typical question in the quiz or exam? Conditions of linearity. And recognize, you may be presented in the quiz three analytical formulas for the least square approach. This is wrong, by the way, okay? And I will need to correct it. And you have to identify the correct one, okay? You are presented like three formulas for least squares, two are wrong and one is correct. And once that I have corrected this, you will see that it's relatively easy. And I may also correct it during the break, so you will get it corrected soon. Okay, and another question may be like assumption of Gaussianity. So you may find like three, what is an assumption for linear trend estimation? And you find three possible answers, two are wrong, and one is Gaussianity, okay? So there is not much to remember. And I dedicated so long time because I am interested in you getting the concept. Okay, so these are two graphs. And now let's talk of another inductive method, run theory, it is nice and interesting. So what is run theory? Let me make a premise. Climate variables typically are affected by cycles. And it is not easy to distinguish the cycles from a trend. And let's get a figure of global temperature. Okay, so let's go here. Let's go to our world in data. Our world in data. And let's get global temperature. Okay, so browse by topic, climate. So it's climate change. Global warming. This is monthly, okay. And this is from 1880. Okay, perfect. Okay, this is the global temperature. This is fine. From 1880 to today. No, not today, January 15. So let's make a zoom here. 1 second. I am zooming in the series. End of 19th century. So if you had only these numbers and you performed here a linear trend estimation, you would have found a decrease in temperature. Actually, when you zoom out, this is just a local cycle. Okay, another one from 1980, or let's say 75, 70, and 1955. Okay, let's go back. Okay, this is what was called global cooling. Okay, so in 1975, more or less, people were much concerned by global cooling, because if you fitted here linear regression, of course, it would be the slope, downward slope, statistically significant. What does it mean, statistically significant? It means that it would be outside of the range of uncertainty. So when you hear somebody saying it's statistically significant, it means that once that you have considered uncertainty, still there is change. Okay. But actually, this is a local cycle because we know what happened later. And even in the recent period during global warming, you see that there are cycles. So this starts from let's say 2008. You see from 2008 to today, this is the famous hiatus. During this period, there was the period was 2010, 2015, 14, and there was the feeling that global warming had stopped. This is called the hiatus. And then in 16, there was a straight increase, and then there was another small, these are monthly data, so you don't have really to look at, I mean, it's not very long, the hiatus that I am pointing out now, but you see that in 2022, indeed, the temperature was low and etc. So how can we distinguish, moral of the story, irreversible change from a local cycle? This is a huge, big question, okay, big question. And so how can we solve it? Okay, let's go back to our purpose. Run theory. Run theory, it is something that has been devised in order to estimate the strength of cycles in a time series. So if you had historical data showing cycles, the idea is to estimate, to to quantify these cycles, to characterize these cycles. How? Okay, the idea is very simple. Let me just try to repeat over the blackboard something similar to that graph. And the run theory is widely used for the estimation of drought behaviors. Why drought? Because with droughts, we have, we are aware that droughts are temporary phenomena typically. Droughts may last for a long time, like 5 years, 10 years. But usually they revert back. And this is why this is the reason why we are not sure, still not sure, whether or not global warming has increased the drought risk. So this is why we try to analyze drought data and characterize these cycles, because we are aware of that. We are aware that global warming is something that is steadily increasing. Droughts are something that they happen, they may last for a long time, and then they cease. And this is the result of the presence of memory in the climate. Memory that we don't understand fully. So the idea is, okay, I have a time series, typically maybe rainfall, but not only rainfall, because droughts may be found in rainfall, and then we call them meteorological droughts. But it may also be that we found a drought in river flow, which is not necessarily related to rainfall. For instance, think of an increased evaporation or a change in snowmelt. Then you may have, even with enough precipitation, you may have a deficit of river flow, and then we call it hydrological drought. Or you may have a deficit in groundwater, and then we call it groundwater drought. So typically, we start from precipitation anyway. So this is precipitation, and a long time. And then you get this, let me identify cycles here, okay? So you may have periods with strong precipitation, and then these cycles. I am exaggerating with the cycles, okay? Okay, so how can we characterize these cycles? First of all, we compute the average of the time series, and this is called, here, we call it RLT. Let's see, RLT, yes, okay. Okay, so now we need to identify two thresholds, one above the average and one below the average. What is the purpose of this threshold? The purpose of the threshold, the lower one, is to mark the start of a drought when precipitation is lower than the threshold. So let me identify the lower threshold. Yeah. And typically the lower threshold is like minus 10%, okay? And I think it is called in the website T lower. Lower. Okay, let's see, T lower. Yeah, T lower. Now, let me identify the upper threshold, and typically it's plus 20%, typically. Sorry, it's two up, so let's put it here. I'm not very coherent with the fact that I said that this is usually minus 10% and this is plus 20. So the scale is not coherent, but I think you understand. Okay, and then once I identify the two thresholds, what I do is to run over the time series. So I start from here. Everything is normal, and here I mark the beginning of a drought. Good. And then the drought starts. So here, drought. Drought. Perfect. And then the drought keeps going. It keeps going, and until the time series goes above the upper threshold. So this is the duration of the drought. But be careful, usually people fix also a minimum number of points above the threshold to close the drought. So in this case, for instance, if this is the number n of data above the threshold, above the upper threshold. So if n is lower than a fixed number n star, then drought is continued. Then drought is continued. And therefore I may go forward up to here. So basically, the parameters that I need to define are, okay, the average is computed, it's not a parameter. T upper, T lower, and then star. And then I can characterize, I can identify the droughts. Of course, if you're interested in flood periods, you look at the cycles above the average. Usually it is used for droughts, and therefore I'm interested in below the average. Okay, now, once I identify the droughts, what are the parameters I am interested in? Because in order to characterize the droughts, I need to identify some behaviors, what I call parameters. First of all, the frequency. So I take the number of droughts divided by the length of the period of the time series, and this is the frequency. It's quite clear. Number of droughts. And then I am interested in the duration. So average duration, or for each drought, the individual duration. So frequency, duration, deficit. During the drought, the cumulative deficit of the variable, precipitation, for instance. Deficit, it means if the drought is longer, the deficit is higher, of course. And then we compute also the intensity. Everything is written there. Intensity is deficit divided by duration. As you can see, it's very simple. And this is a way to, once again, characterize cycles. So why it is relevant? For instance, think of a series that presents cycles with duration of like 30 years. This sometimes happens. The global temperature is like 30 years. Now, if in the same series you see an increasing trend that is lasting 10 years, you may say that the length of the trend is still comparable to the length of the cycles, the historical cycles, and therefore it may be a cycle. And also you look at the slope of the trend. and you look at the intensity in a way. The slope of the trend quantifies intensity. So you compare the intensity of the past droughts with the slope of the trend. So characterizing cycles is extremely important. Okay, I think let's stop here because this final part is for the next time. And next hour, I will focus on the exercise that I opened the last time just for reading the text. And we will dedicate with R the time to the next hour to the solution of the exercise. Do you have any question before we stop for 15 minutes? Yeah. N star is the length of the period above the upper threshold required for stopping the drought. So, for instance, if you have a drought that is lasting 10 years and you have only 1 year with precipitation above the upper threshold, and then another drought starts, then you put the two droughts together. You don't stop it. In order to stop the cycle, you require that the cycle is interrupted for a minimum number n star of data. Is it clear? No. Okay, so let me just make a numerical example. Or let me make a graph that is clearer. Okay, let me start with, this is the variable PP, and this is T. Let me start with RLD, placed here, RLD, and let me just put there the two thresholds. This is T upper, this is T lower. Okay, good. Now let's start with our numbers. Let's suppose that we have an observation here, okay? And then we have another observation here. The drought starts, okay, correct, perfect. And then the drought goes here, is continuing, goes here, is continuing, and then I get a number here, which is above the upper threshold, but it is only one, and then I get something like here, okay? Or let's say here. Okay, so I'm below the threshold. Okay, the drought is not interrupted, is continued. And then it may be here, and then I go up, and then here I get other two numbers like this. And here it is interrupted. If interrupted, let's suppose that n star is equal to 3. So here you got only one number above, it's not interrupted. It is interrupted here. This is the drought duration. It is interrupted here because it's 1, 2, 3, and then it is interrupted. Or let's say it is interrupted here. It is interrupted here, but you get the condition is that you don't interrupt it the first time. You wait for 2 more points. And here, if you waited, you didn't get another above the threshold, and then, is it clear now? Okay, good. Let's make 15 minutes break. Thank you. Okay, so okay, so computation of risk associated to flood events. Let's elaborate this example of application of the risk equation. So this is the text of the exercise, which we already read the last time. Let's have a look quickly. So computation of risk associated to flood events. We are given a series of annual maximum peak flow for a river, okay, and we are given 150 numbers of annual maximum peak flow. So this means that the period covered by the data is 150 years, which is quite a long period. And then the river is protected by levees so that vulnerability is kept to zero up to a river flow of about 12,000 cubic meters per second. Then vulnerability is increased linearly to 1 for a peak flow of 18,000. And you see the vulnerability graph, which is similar to what we have considered during the lecture. And then we have exposure here. And with these numbers, exposure, it's 0 up to 8,000 cubic meters per second, and then there is a linear increase to a value of 12 million euros for a river flow of 16,000. Okay, now we need to compute and plot in a graph the risk associated to flood events for peak flow ranging from 0 to 30,000 cubic meters per second. So we are suggested to compute the hazard probability P with the log normal probability distribution, and we use the probability of not exceedance to estimate P and make a reasoning of the meaning of the obtaining risk values. What do they mean? Because we can use, of course, the probability of not exceedance or the probability of exceedance in order to compute the risk, but the result that we obtain is different. So, and then we have to make a reasoning on the meaning of the risk computed with the probability of not exceedance or probability of exceedance. Okay, now we have a suggested R code here, which I propose to use. Let me click on it, and this is the R code. Okay. Now, first of all, let's open an RStudio. I need to open it not locally because I cannot install RStudio on this PC. And so this is opened remotely. One thing, I need to download also on the remote computer the series of the max annual maximum peak flow. Second, here we are. So I need to download the file, just 1 second, even here. And the computation of risk, here is the file. And then I save on my desktop this file. Okay, let's have a look at this file just in order to understand what we are talking about. So It is saved here on the desktop. I should find it. Okay. And I open it with the text editor. You see that it is a sequence of 150 numbers. Okay. And this is annual maximum peak flow. I need to upload it into R. So let me just go into RStudio, and then let me select the directory, session, set working directory to desktop, and it's, sorry, session, set working directory, choose directory, sorry, desktop. Here we are, choose, perfect. I clean the console, and then we can scan here. So let's call it Maxan equals scan, and then I take the file, and then it's 150 items. Very good. Let's make a plot of it. Plot Maxan type equal to line. Okay, good. The plot is made anytime we think it is appropriate to check the data. And actually, I think this time series is just fine. Okay, now we need to compute the risk associated to river flow ranging from 0 to 30,000 cubic meters per second. In order to compute the risk, we have already available the vulnerability and exposure. We need then to compute now the probability of not exceedance. We are told probability of not exceedance of peak river flow ranging from 0 to 30,000 cubic meters per second. And we are suggested to use the log normal distribution to compute the probability of not exceedance. The log normal distribution is to be estimated on the series Maxan annual maximum peak flow. Now, the log normal probability distribution has two parameters. The two parameters are the mean of the data and the standard deviation. Therefore, we need to compute, just to compute the mean of the time series, the mean of the logarithm, sorry, of the time series, maxan.txt, the time series of the annual maxima, and the standard deviation of the logarithm. So the estimation is very simple. Fitting the probability distribution is very simple. We just need to compute mean and standard deviation of the data, and that's fine. We are not required to check if the probability distribution fits the data well. We are not required that. So we just need to compute the parameters. And by using this probability distribution, these two parameters, we need to compute the probability of not exceedance of this sequence of river flows from 0 to 30,000. Okay. So first of all, let's move forward with this, and let's first fit the probability distribution. Okay, first let me just check the syntax of the function PL norm. The function PL norm is used, we will use it in order to compute the probability of not exceedance of our data, of the data, the sequence of river flows from 0 to 30,000. And so basically you see that this is the usage of the function. And you see that we have to give the mean as parameters, the mean of the logarithm and the standard deviation of the logarithm. Okay, very good. Now, first, let's build the sequence of the data that for which we have to estimate the probability of not exceedance. I'm not looking at the suggested R code. So what I'm writing here may be different from what is written in the suggested R code, but the concept is the same, okay? So first, let's simulate river flow as a sequence from, remember the text, from 0 to 30,000 cubic meters per second. So it's a sequence from 0 to 30,000. Let's make, let's use a step of I would say 100 in order to minimize the number of computations that we have to do. So the sequence that we get, river flow, it's the one that you see here. Starts from 0, 0, 100, 200, 300, and then we have the last number, which is 30,000, and the total length of this sequence, length of river flow, should be 301. 301, perfect. Now we need to compute the probability of not exceedance of this time series that I created. Okay, this series, not really time series, it's a series. So let's call P, it's equal to PL norm. Look at the, on the right, the help there. PL norm of what? We need to give river flow as an argument, river flow. And then we need to give the standard, the mean of the logarithm. So mean logarithm maxan. Okay, and then the standard deviation as the log maxan. Okay, the obtained vector starts from probability of not exceedance probability of not exceedance of 0. Probability of not exceedance of 0 should be very close to 0. And then increasing, let's check it. Okay, let's plot it because it's easier. Plot P type equal line. Okay, this is the plot. So you see it starts from 0. This is probability, again, of not exceedance, and then it goes very close to 1. Okay. We can also plot the density if we want. Plot the density may be plotted in this way. It's plot. I would say the density is the difference, is the derivative of it. So let's make plot river flow. First of all, I have to give the horizontal axis, the x-axis, river flow, but I think we need to start from 2 and then get to 30,000 to 301. And then in the vertical axis, we put the density. In order to compute the density, let's make the derivative, the difference of P. I think this should give, as a result, the plot of the density. Let's see if I made it correctly. Yes, this is the density. It's typical of the log normal distribution. So once again, in this instruction, I put the river flow on the horizontal axis, as it should be done. And in the vertical axis, I put the difference, the function diff computes the difference between two subsequent elements of a vector. and therefore it's a derivative. Look, river flow is extended from 2 to 301. So I am removing the first element of the vector of the horizontal axis, because when I compute the derivative, the difference, the first element of the vector is lost. When I compute a difference, of course, of a vector, if the vector is 10 numbers long, the vector of the differences is 9 numbers long. So this is why the horizontal axis has been limited in length from the second element to the last one. I hope it's clear. Okay. So the moral of the story is that I computed the probability, capital P, of not exceedance for the simulated sequence of river flow from 0 to 30,000. Now I have to compute for each of this river flow the product of probability of not exceedance. It's in this vector. It's in the vector P. Okay, it is in this vector, times vulnerability times exposure. Good. However, just one second, vulnerability and exposure are given by these functions here, which I need to translate into R. So I need to give a numerical and analytical numerical expression of these functions into R. Okay, these are piecewise linear functions, so it is easy to put into R these graphs. How to do that? Let's refer here. Create a vector of vulnerability and exposure. Perfect. So let's create the vector of vulnerability and exposure then. So first of all, I need to define these two vectors, vulnerability and exposure, and it's like a repetition of 0. So I copy this, and I go into RStudio. Let's see. I hope that it works, the cut and paste from different computers. Probably not. Okay. Okay, no, it works. Okay, and these vectors are just, if you look, for instance, at exposure, it's just a sequence of zeros up to now. Now I have to put the linear function into these vectors. So it's, one second. Create interpolated vector of vulnerability. You see that basically it's a sequence of 0 up to the 12,000, and then there is a linear increase. This is a linear function of increase. So let's copy this, and let's go here. One second. I don't find it. Oh, here it is. I'm sorry. Okay, paste. Okay, you see the plot already on the right. It is the same plot that I got from the PDF text of the exercise. It is simply put into here. Okay, it's just a piecewise linear function, and you see the instruction on the left. Okay, now we have to make the same thing for exposure. Look, and remember, vulnerability is varying from 0 to 1. Exposure is varying into a not predefined range, because exposure is measured in economic value. So it's the range is not predefined. Okay, let me clear the console. Perfect. And let's go here. Create interpolated vector of exposure, and then let's get the plot. Okay. Okay. And this is the plot of exposure. Okay, good. Now we are ready to compute risk is equal to P times vulnerability times exposure computed. Very simple. Let's plot risk now. Plot risk type equal line. Okay, this is the risk. Good. Now, now the question is, let's think at the meaning of what we found, because what we found is slightly different with respect to what we have seen in the documents, in the lecture notes. So first of all, keep in mind, this is the computation of risk depending on the probability of not exceedance for a continuous variable. So what does this mean? So take a predefined value of the river flow, like the river flow is not plotted here in the horizontal axis. Let me plot it. Plot river flow and risk. River flow, risk. Okay, now we get the river flow here, okay? So let's take, for instance, the river flow of 15,000, AB line V equal 15,000, call equal to red, and line width equal 5. Okay, let's take the river flow of 15,000. It has been obtained by multiplying vulnerability and exposure times the probability of not exceedance of the river flow, which means that the risk, the resulting risk, is the integration of all the events that have that are lower or equal to 15,000. So it is, once again, the integral of the risk for all the events that are varying from 0 to 15,000, lower than 15,000. So this is the damage caused by the events that are lower or equal than 15,000. Okay? If I took the probability of exceedance, it would be the expected damage for all the events that are higher than 15,000. Okay. So basically, if I want to estimate what is the river flow that gives the maximum increment of the risk, so the river flow that corresponds to the max increment of the risk, I need to plot the difference of it. So if I make plot diff river flow, yeah, okay. Risk should be from 2 to 301. And just 1 second, because yeah, it is corresponding to 100. Just 1 second, because there is a problem of a scale of representation. So it is giving. Okay, let's get the previous plot. Sorry, because in this way it's not clear. Just 1 second. If yeah, I made the difference of river flow, not of, okay. The mistake was that in this instruction, let me go back. In this instruction, I took the derivative of the river flow, not of the risk. Instead, I had to take the derivative of the risk. And if I take the derivative of the river flow, the derivative of the river flow is 300, is constant. So the probability density gives a delta function in the correspondence of only one value. So it is not what I had to compute, but what I had to compute is the difference of the risk. Plot river flow from 2 to 301, and then difference of the risk. And here, I think, okay. Now, if I didn't make any mistake, it should be perfect, okay? And now this is the critical river flow is, or let's say, let me just put the river flow on the horizontal axis, which is, yeah, it's river flow. It is around 15,000. This is the max of the increment of the risk. So the type of event that gives I mean, the max of the increment of the risk is around 15,000, and then we have a decrease of the risk. Okay, so the max of the risk is around 15,000. This is what I meant to say when I said think at the meaning of it. If you use the probability of not exceedance or the probability of exceedance for a continuous variable, like in this case, you get the risk associated to all the events that are lower than a given threshold or higher than a given threshold. And it's not only one event, because one event is for discrete variables. For this kind of probability of not exceedance, it's if you use the probability of not exceedance, you get the risk associated to all the events that are lower than the considered one. Instead, if you take the difference of the risk, meaning that you take the difference of the probability of not exceedance, you get a curve that is similar to what we found in the lecture notes. That's it. Okay. Now, this is an exercise that is simple in terms of computation, but the interpretation requires a kind of effort on your side. And this is why I put the note, try to think at what is the meaning of what you found, because in the lecture notes, we referred to a single event, a discrete event, and then the probability of a single event. Here, we are using the probability of not exceedance, which is the cumulative probability. So it requires on your side a different interpretation, which is something that I want to stimulate to you. And this is why I wanted also to make it in physical presence, because I think this different interpretation requires some effort. Okay, try to elaborate on it, because it is not really important for the exam. For the exam, when you are asked the risk equation, you can just say probability of an event, a discrete event, which is not the cumulative probability of not exceedance. On the other hand, I want that you get the difference when, with respect to the lecture notes, where you use the probability of a given event, which is in a way for discrete variables, If you use the probability of not exceedance for a continuous variable, it's a different story. And this is why I wanted to propose you in an exercise. It's not written in the lecture notes because it's not something that I want you to study for the exam, but it is something that I want you to try to understand. Okay, any question? Okay, give me, before we close the lecture, give me 5 minutes, okay? And let me just 1 second, because, okay, fine. Okay, the code that you find on the website is similar, but of course, it doesn't make any elaboration on the result. But you see that indeed here there is the computation of, let me just make it, because it's a bit different of the computation of the density. Let me just put it on, it's a bit different with respect to what I did. So let me put it here. 1 second. Okay. Peer river flow not found. Yeah, okay. Okay. Let me just, because I use different names of the variables, so it's a bit different. It's P, okay. 1 second. One second. Okay, this is what we got earlier. Okay, very good. So you have the code here. Of course, as I said, there is no interpretation. And now let me just go back a little bit and let me check whether I completed everything. Yes, okay, this is perfect. Okay, so just a reminder, we meet online on Thursday, and then we have 1 week break. Okay, so we will see each other again in presence Monday, April 22nd. There is no lecture on, of course, on the 25th of April, because I am abroad, but it was also an holiday. And on Monday, April 22nd, we will have a presentation by one of your colleagues, and then we will have another presentation, I think, after 1 week or 2 weeks. Anyway, just to remind you that if you are willing to deliver presentations, it's you have to take the opportunity now. And okay, perfect. Thank you very much. Any question? Okay, good. Thank you.